In section 11.3, I'm going to do some more numerical examples involving problems concerning universal gravitation. In this example, we're going to consider a 50-kilogram student, and part A wants to know what is the student's weight when standing on the Earth's surface. So we're going to do this the long way, where we're just going to plug in the numbers to the equation and use that to calculate the force of gravity, aka weight. We're going to use Newton's universal law of gravitation, and we're going to take the distance from the student to the center of the Earth is the radius of the Earth. And we typically use capital letter R to indicate that the radius that we're using is the radius of the planet itself. So G is that universal constant. It always has that same value. The mass of the student is given as 50, and the mass of the Earth is given right here, 5.97 times 10 to the 24th kilograms. And we're going to divide that by the radius of the Earth, which is also given right here, 6.37 million meters. And when we calculate that, we'll get a force of 491 newtons. Now, for part B, if the student uses a hoverboard to rise to a height of 8.2 million meters above Earth's surface, what is that student's weight? So again, we're going to use Newton's law of universal gravitation, but now the distance to the center of the Earth is no longer going to equal the radius of the Earth, so we're going to switch back to lowercase letter r. Now, when we measure the distance to the center of the planet, we're going to have to add the radius of the planet, which is 6.37 million miles, or meters rather, to the distance from the surface, which is given as 8.2 million meters. So this works out to be 14.57 million meters. Remember, when we measure the distance between the objects, we are measuring the distance from the center. So the numerator is not changing. The denominator is changing to a larger value, so we should expect that the student weighs less when further from Earth. And we end up getting 93.7 newtons. I performed that last example just using a plug and chug method. I used the law of universal gravitation, took the values given, and then crunched the numbers to get my answers, which is a perfectly fine way to go about solving the problem, but we can be a little bit more sophisticated and work smarter, not harder. So part A is very straightforward. We're trying to find the weight on Earth's surface. So weight, we know, is mass times the strength of gravity. We have a value for the mass of 50, and if we use a value of 10, we would get 500 newtons. If we used a value of 9.8, which is more accurate to Earth's strength of gravity, we would get 490 newtons. And part A, the answer that I gave on the last slide was 491. So this is probably a decently accurate answer for the problem. Now for part B, now we're moving up to that new height. And remember, the new height, or the new distance rather, the distance on our hoverboard was 14.57 million meters. And if I take that and I divide by the radius of the Earth, The radius of the Earth was 6.37 million meters. So the million meters on top and the million meters on the bottom cancel out, and that gives us a ratio of 2.29. So when we're on our hoverboard, we're 2.29 times further from the center of Earth than we are at the surface. And if we remember that the force of gravity is inversely proportional to the distance squared, we can set up that ratio where the force of gravity on our hoverboard, that fraction of the force of gravity on Earth's surface, if I take this ratio that I just found, the 2.29, and I square it and I put it on the denominator to reflect that it's inversely proportional, then I will end up solving for the force on the hoverboard as 95.3, which is just a little bit more than the 93.7 that we did on the last slide. There's some little bit of an error there just because we're rounding very large numbers to only 3 digits. In the next example that I'm going to do, I'm going to look at the force of gravity acting on a satellite in orbit. And before I do that, I want to briefly discuss orbiting objects. An orbiting object is in free fall. The only force acting on it in space is gravity, and that situation is what we describe as free fall. The acceleration of an object in free fall is g, but remember that g is only 10 on the surface of the Earth, and so that acceleration is probably less than 10. We should also remember that objects in free fall are weightless. So an astronaut orbiting on the International Space Station is going to be experiencing weightlessness. Now, I'm going to use some vocabulary when discussing orbiting objects. The object that does the orbiting is what I'm going to refer to as the satellite. The object that is orbited by the satellite, I'm going to refer to that as the central object. So in the case of the moon orbiting the Earth, the moon is the satellite, the Earth is the central object. In Earth's orbit around the sun, Earth is the satellite and the sun is the central object. We should note that orbital properties, the properties that define a satellite's orbit, its period, how long it takes to go around its central object, and its radius depend only on the mass of the central body and the speed of the satellite. It does not depend on the mass of the satellite. The mass of the satellite does not matter for the properties of its orbit. Now, why don't satellites just crash into Earth? Doesn't gravity pull the satellite towards Earth? Well, yes, it does. And there's a nice explanation for why a satellite doesn't just fall into the Earth. And Newton is also credited with this idea. In Principia, he drew a similar picture to what you see here, and this is described as Newton's cannonball. It's a thought experiment proposed by Isaac Newton. In it, he imagined a cannon on top of a very, very tall mountain that can fire the cannon. That can fire the cannonball sideways at different speeds, and he imagined that the Earth didn't have any atmosphere, so the cannonball wouldn't experience any drag. It would just be in free fall. And the trajectory of the cannonball, the path that it took, depended on how fast the cannonball was fired. The path depended on the cannonball's speed. And you can see here that paths A and B, the cannonball falls down to the surface of the Earth. In path B, the cannonball was fired faster than in path A, and so it went further before hitting the surface, but they both fell to the Earth. Paths A and B are showing what happens when the satellite isn't moving fast enough to achieve orbit. It falls into the Earth in a parabolic path, what we described as a projectile. Path C shows just the right speed to achieve a circular orbit. Circular orbit is the special speed where instead of falling into the Earth, when the cannonball curves down, it curves down at the same rate that Earth's surface curves. And so instead of falling into Earth, it falls around the Earth, maintaining the same distance from Earth the entire orbit. And if it gets fired a little bit faster, it'll follow path D. Path D shows an orbit, but it's a little bit different. It's in the shape of an ellipse. And if the cannonball is fired really, really fast enough to escape the Earth's gravity, we would refer to that as an escape trajectory. And escape trajectories have a particular mathematical shape called a hyperbola. And here you can see some animations of those four paths. Top left shows the parabolic path that we would describe as a projectile. Top right shows that special speed that achieves a circular orbit. Lower left shows an elliptical orbit, so it's fired faster than a circular orbit. So it still orbits the Earth, but now it's going to go in an ellipse. And if it's fired very fast, then it follows an escape trajectory or a hyperbola. And it should be noted that all of these shapes are very special mathematical shapes. They are described as conical sections. If you take a cone and you split it in different ways, it will cut out these four shapes: the circle, ellipse, parabola, and hyperbola that we see. And this all has to do with the mathematical nature of gravity, that being that inverse square law gives us these particular shapes. So in this example, I'm going to go through some of the math for a satellite of mass lowercase m. Notice that's not given. We're going to expect that to cancel out. For a satellite at an altitude of 35,800 kilometers from an altitude is the distance from the surface. So part A wants us to find the acceleration. So the acceleration, as stated before, is going to equal g, and we had found a formula for g. Lowercase g is uppercase g times the mass of the source of gravity. In this case, it's going to be the mass of the Earth, divided by the distance from the Earth's center squared. And because we weren't given the distance from Earth's center, we should calculate that. The distance from Earth's center is going to be 35,800 kilometers. Add 3 zeros to turn it into meters, and then we have to add in the radius of Earth, 6.37 million meters, and that will give us a value for R of 42.17 million meters. Okay, so now I'm ready to plug in all my values. G is always the same value, 6.67 times 10 to the minus 11th. We're using the mass of the Earth here, 5.97 times 10 to the 24th kilograms. And we're going to divide this by our distance from Earth's center, 4.217 times 10 to the 7th meters. Don't forget to square it. And that is going to give us an acceleration of 0.224 meters per second squared. Notice it's not 10. We just calculated g, we didn't get 10. For part B, we want to know the speed of this satellite. So this acceleration that we just found is an centripetal acceleration because our satellite is in circular orbit. And centripetal acceleration is speed squared over radius. I can solve this for speed. It's acceleration times radius underneath the square root. I know my value for the acceleration. I know my value for the radius. Don't forget to take the square root. And we end up getting a speed of 3,070 meters per second, which is just about 6,900 miles per hour. And this is a very, very special speed. It's a very, very special speed for satellites around Earth because it gives a very special period. That speed is distance over time. And the distance that a satellite would travel in a circular orbit is the circumference of that circle. If I solve this for period, I get 2 pi r over speed. I know that radius, that's the 4.217 times 10 to the 7th meters, divided by that special speed, 3,070 meters per second. That is going to give us a value of 86,300 seconds. And what's special about that period in hours is exactly 24 hours. And why is that an important period? Well, because that's the period of Earth rotating on its axis. That's a day. And we use satellites like this. We have to put it in circular orbit, which means that it maintains the same altitude, same distance from Earth's surface, and it rotates with the same period of Earth. And so that puts it in what's known as geosynchronous orbit. Geo meaning Earth, sync meaning same, and chrono meaning time. Same time as Earth. It has the same period of rotation as Earth. And so that satellite is going to maintain a constant location above the same place on Earth's surface. And that is really, really important for communication satellites. And because it puts it in what's known as geostationary orbit, where it not only occurs at the orbits around the equator. And you can see this graphic. These are all the satellites around Earth, and you see that there's a big concentration of them in what almost looks like a belt, right around here. Those are all of the geostationary satellites that we have around Earth, and they're important for communication. Where we use them for TV, like anybody that has a satellite television, like DirecTV, you're looking at a geostationary satellite. We use this for GPS. We use this for cell phones. So putting a satellite in the right place with the right speed is super critical for all of our communication.